Dạ, ừ. Hey, Matthew. You have any questions before we get started?
Hey, Professor. No questions. I have two questions on the homework for chapter 17. Is
Hmm.
that kind of an office hours thing after the session today?
Yeah. I also can have time before class, but yeah, it would be a little better if we started if we did it right after.
Okay, sounds good. And truth be told, I haven't got to the chapter 18 material yet, so therefore I don't have
Gotcha.
any questions. I'll be an active listener, however, and try to follow along as much as possible.
That sounds good. And actually, remember, I skipped a lot of coverage of sections from chapter 17. Today, I've been making videos for those. I'll be making some more
Okay,
tomorrow. I think I posted two already, and I've got like four more sitting by the wayside. So, two have been done on yeah, two have been done on linear expansion. I've got another one on linear expansion that's a little more complicated, and then I have a couple ideal gas law ones that are going to happen. So we're going to
okay,
start
great.
off as if we know all that stuff in chapter 18, though.
Yeah, okay, great.
All right. All right. Well, let's go ahead and get started. It's 2 minutes after, and again, I do treat attendance here as kind of optional, meaning I'm not going to punish anybody or anything for missing, but I am still supposed to, like, if you guys miss 2 or 3 days in a row, by the time you miss 4 days in a row, I'm supposed to go ahead and drop you. So make sure you keep me in the loop if you do decide that you're going to miss a few classes. Like I said, I don't mind you missing classes. But it does happen, and when it happens, it's not necessarily the easiest way to learn, especially with a 242 class like you're in right now. Taking 242 online without interacting with your instructor is going to be near impossible. So attend as much as you can, but if you can't, that's just fine. I'm not going to harm you, and hopefully you can still do well. So we're getting started today on chapter 18. We had done chapter 17 last week. I'm actually looking for, there it is. I'm trying to set up my appropriate file for this class. I think I got it now. Yeah, I got it. So I'm just going to change the name real quick because I realized I didn't change it uh, because I thought I'd already did it, but that was me remembering the videos I just made. So today is the 21st. So today's file is going to be PHY2420, or excuse me, 242005B underscore 01212025. So that is the file today, and that's basically the date you look up to find the actual notes in my Google Docs. All right, now I'm duplicating that so I can use it next time. And now I have the actual documentation open. So what I'm going to do is I want to start off just showing you a little bit about what chapter 18 is about. So I'm going to go ahead and share my screen with you guys. Oops, evidently I'm trying to share my screen with you guys. So let me do that real quick. So this is on the kinetic theory of gases. And the first thing I normally do in this chapter is I would go through and derive the actual expression, excuse me, for the average kinetic energy of the molecules in an ideal gas. And they'll open up telling you what the uh, sort of what the behavior of molecules in an ideal gas are. And we sort of use the term molecule and atom interchangeably here. So you'll keep hearing me say atoms or molecules. Just remember on virtually all that stuff I'm talking about, atom or molecule would be an acceptable phrase. But the main thing is there's very specific ideas. So what I haven't yawned all day and all of a sudden I've got yawns. Uh, but the main thing is there's a concept of what an ideal gas is, and we're going to make those assumptions. And I'm just going to take the results because you can look on my YouTube channel or any of the videos I've tagged and see where I actually derive the expression for the kinetic energy of the molecules or atoms within an ideal gas. And I'm just going to start using those instead of doing the derivation. So if you're curious, about how the derivation is done. For starters, you definitely should be reading how it's done. In principle, the highest hanging fruit within this class is probably your ability to derive the expressions that the textbook derives. So you want to ideally aspire to be able to do that, but that's a little harder than I necessarily expect my students to do. But you still derive a good deal of insight by knowing how the derivations take place. So definitely read over it, look over my versions of it, and see if it makes any sense. Uh, in chapter 18, the very first section is called the ideal gas law and molecular interpretation of temperature. 18.2 is distribution. There goes the yawning again. Distribution of molecular speeds. 18.3 is real gases and change of phase. 18.4 is vapor pressure and humidity. I generally, by the way, skip that section. So completely cool for those problems to be in homework, completely cool for those problems to be in the practice test, but I'm not going to be having those on the actual test. So if you find one on the actual test, let me know it's there, and then you'll automatically get full credit for it. As a right answer, no matter what you did. But we're skipping that. 18.5, temperature decrease of boiling water with altitude. 18.6 is van der Waals equation of state. 18.7 is mean free path, and 18.8 is diffusion. Generally speaking, I also do the easiest of the van der Waals equation of state problems. So just ones where I give you the parameters A and B, or in some cases there's just one parameter, and then you solve it like an ideal gas law. Yeah. Like an ideal gas law problem, but that's about the extent of what you need for the van der Waals equation. The free path, again, that's a derivation that I find very useful. But again, that and diffusion, I'm not going to require you to be able to do that at all in the test, but the homeworks are fair game. So let's go ahead and get started. The chapter test, or the chapter, does have an opening question, and you should always try to answer those before we start. No matter whether you say it out loud or not. So, for instance, they're asking, what do you think the typical speed of an air molecule at room temperature is? And they're asking you for, do you think it's less than 10 kilometers per hour, on the order of 10 kilometers per hour, on the order of 100 kilometers per hour, on the order of 1,000 kilometers per hour, or near the speed of light? Okay, so that's a poke you should take. That's a guess you should make. And then as you find out later when you start to do the calculations, then I want you to correct your knowledge or pat yourself on the back for getting the right answer. So always do that with every chapter. The answer is shortly thereafter given, usually within the body of the text, but also I think there's a place either at the end of the chapter or at the back of the book, but I think it's the end of the chapter. So here's the four uh, criteria for the way atoms or molecules behave in an ideal gas. There are a large number of molecules, capital N, each of mass, lowercase m, moving in random directions with a variety of speeds. This assumption agrees with our observation that a gas fills its container and, in the case of air on Earth, is kept from escaping only by the force of gravity. Two, the molecules are, on average, far apart from one another. That is, their average separation is much greater than the diameter of each molecule. Three, the molecules are assumed to obey the laws of classical mechanics and are assumed to interact with one another only when they collide. Although molecules exert weak attractive forces on each other between collisions, the potential energy associated with these forces is small compared to the kinetic energy. So we basically go on the assumption that the potential energy is zero. Four, collisions with another molecule or the wall of the vessel are assumed to be perfectly elastic, like the collisions of perfectly elastic billiard balls that we covered in chapter 9. We assume the collisions are of very short duration compared to the time between collisions. Then we can ignore the potential energy associated with collisions in comparison to the kinetic energy between the collisions. So that's the way that's done. You can start off with those premises and then just treat molecules as if they're point particles. And you imagine this guy has an x component of velocity, which would be left, right. It's also got a z component, which would be in and out of the page, and also has a y component, which would be up and down. But oh, if you examine just one dimension first, you can get an idea of roughly what or you can call the speed Vx, and then slowly we can work out what the ultimate average is. And that's what this derivation is about. I'm going to jump right through this and go into the examples. what we finally see is this result right here, the average kinetic energy. There's a couple ways we can write average. In one case, you put a bar over it, and that means average. In another case, you can actually put less than on the left-hand side and greater than on the right-hand side, and that's another average as well. I'll be using those interchangeably. But one thing you want to see is that the average kinetic energy, which remember kinetic energy is defined to be 1/2 mv squared. So the average kinetic energy turns out to be 1/2 m times the square of the uh, velocity, the root mean square velocity that we calculate. And then that turns out to be equal to 3/2 kT. So that 3/2 kT is what allows us to figure out the individual velocities, whereas the kinetic energy is just 1/2 m times the root mean square velocity, which we subscript with the RMS. And since it's root mean square, you might realize that we're taking the uh, average of the square of the velocities, and when we're taking the square root of that. And therefore, once you square it, then you have what can be multiplied by 1/2 m. So the average translational kinetic energy of molecules in random motion in an ideal gas is directly proportional to the absolute temperature of the gas. So what you can see here is if you canceled out the 1/2 and the 3/2 on the left and right of the two parts there, ignoring the K bar, the twos would cancel out, and what you get is V squared bar is equal to 3 kT over m. If you take the square root of both sides, you get the root mean square velocity is equal to the square root of 3 kT over m. And that's what I mean by it's just the average kinetic energy is just a multiplier away from the actual temperature of the gas. So let's start with this example one. What is the average translational kinetic energy of molecules in an ideal gas? This is example 18.1, and we're going to work that. So let's start here. And I'm going to share my screen in a second. So this is example 18.1. They want to know what is K bar uh, for the ideal gas at 37.0 degrees Celsius. I added an extra sig fig there. So what I'm going to do now is I'm going to go ahead and stop sharing the screen of the page and start sharing my iPad screen. So here we go. Okay, so that should be coming up any second now. So that's our question. Example 18.1, what is the average kinetic energy? And specifically, they're saying the average translational kinetic energy. So I should probably mention that. Average translational translational kinetic energy. Okay, that's what they're asking for here. I got another person that just logged in. So the reason why I stressed that, and I didn't write it down initially, of course, but the reason why I'm stressing it now is I want you to realize by missing the derivation, you didn't necessarily get this part. But what we calculated was the average random translational kinetic energy of the individual molecules. And what I mean by translational is remember the 1/2 mv squared term in conservation of energy. But we also had a 1/2 mv squared term that could be part of it. Where you're actually taking the center of mass of the molecule, moving it at a velocity v with a mass m. But there's another part where the molecule could, in some sense, be spinning around an axis or bouncing back and forth around some central point, all that kind of stuff. Those are different types of kinetic energy, and those are not ones that directly affect the temperature. So what I want to say here is the equation we're using, according to the solution, is the average kinetic energy, K bar, is equal to 1/2 mv squared bar, and that's equal to 3/2 kT. And what I mean by that is this V bar is really the average of the squares of the velocities. And of course, I've already mentioned that that would be root mean square. And I'll show you how to calculate a root mean square in a second. So we have this formula for the average translational kinetic energy, K bar. As I said, if the molecule, for instance, was diatomic, for instance, H2 or O2 are diatomic molecules, and if they have the right amount of energy, then the two oxygens or the two nitrogens or the two hydrogens would more or less be like a pair of dumbbells. You'd have a bulbous atom on one end, a bulbous atom on the other end. In fact, the two atoms are in fact identical because they're both atoms of that gas, which in the case of H2 would be two hydrogens, or O2 would be two oxygens, or N2 would be two nitrogens. And they in fact can rotate like this, but that's not translational kinetic energy. They could also rotate like this. That's not translational kinetic energy. And then there's a third dimension they could rotate, which is about that. But that one actually turns out to be really insignificant because the size of the atom is so small, the kinetic energy it gets from that would be minuscule. But we are, in fact, cutting out the ability to get the velocity, the average velocity, as a result of it rotating this way, or as a result of it rotating this way. They're not playing in this at all. We're just talking about this whole atom or molecule going this way, which is one dimension, this way back and forth, which is another dimension, or this way, which is up and down, which is the third perpendicular direction. So let me show you how you're going to go ahead and do this. The average random kinetic energy is K bar, and K bar is equal to 3/2 kT, and K is what we call the Boltzmann constant. K, and I usually write it, in fact, K sub B. But the main thing is you got to know what that value is. So what we're going to do is we're going to put 3/2 and then the Boltzmann constant, which is 1.3807 times 10 to the negative 23rd joules per Kelvin. Now, if you read chapter 17, you probably know where this Boltzmann constant came from, but it's basically like Avogadro's number divided by the R from the ideal gas law, or somewhere around there. And I might be misremembering that slightly, so I forgot to look back at it beforehand. But there's the K that we're using. I actually generally use all 5 of these sig figs just because that's what I have memorized, but you don't have to do that. Now I've got to put in the temperature, and the key thing about using this formula is, and this is part of what you would have gotten from the derivation, is you have to use the temperature in Kelvin. So when we say 37 degrees Celsius, we're not allowed to use that at all. We have to use 273 plus 37. So when we add 273, and we add 30 to it, that's going to give you 303. And then when we add another 7 to it, that's going to be 310. So we get 310 Kelvin, and notice no degree mark is on there. It's just 310 Kelvin. And now we can do the calculation. It's going to be 3/2, which is 1.5, times 1.3807 times 10 to the negative 23rd times 310. And that's going to give me 6.42 times 10 to the negative 21, and, or excuse me, 10 to the, 10 to the negative 21, and that comes out automatically in joules. Okay, so that's the kinetic energy of the molecules are atoms, depending on what you're working for. In this case, when you're talking about air, the two most likely components of air are obviously oxygen at 20% and nitrogen at near 80%. And both of those are diatomic, of course. So there's our answer to example 18.1. And hopefully that seems pretty reasonable to you. Your book makes a point to tell you that that, in fact, is basically if you took a mole of these molecules and tried to figure out how much energy they would have, just one mole, which remember, I say just, but just means 6.02 times 10 to the 23rd individual atoms, or in this case, molecules, if we're talking about oxygen or nitrogen. So if you took a mole of them, that would be 3,860 joules, which is about the kinetic energy of a 1 kilogram stone thrown at 90 meters per second. So it really is a lot of energy associated with the thermal agitation of atoms and molecules. The next example we want to work is uh, a little more incisive, or basically just allows us to probe a little deeper. So in this case, what we're wanting to figure out is what is the root mean square speed of the molecules of oxygen and nitrogen, okay? And this is the root mean square speed of their translational motion. So I'm going to start with example. I'm just going to call it example two. In some cases, they'll look a lot like the examples from the book. In other cases, they're going to be like it, but just slightly different numbers. So, what is the translational root mean square velocity of the molecules of O2 and N2 at room temperature? And of course, part of this is just to remind you that we do use room temperature, and room temperature is supposed to correspond to 20.0 degrees Celsius. Okay, so that's our problem. This time we're going to use again K bar, which equals 1/2 mv bar, or v squared bar, but that's equal to 3/2 kT. Okay, so if we just take the right two parts, then we get 1/2 mv squared bar is equal to 3/2 kT, which means v root mean square is going to equal the square root of 3 kT over m, where m is actually the mass of the individual molecule. So if we look at the periodic table, what we see is the molecular weight, or in this case, the atomic weight of oxygen, is essentially 16. And we used to call that grams per mole, which would be right. But as of chapter 17, we learned that that was also the weight of a single atom, but we'd use the units of U. Therefore, the molecular weight of O2, which is how oxygen naturally appears in our atmosphere, is actually equal to 32 U, which equals 32 times 1.6605 times 10 to the negative 27th kilograms. Okay, so if I multiply that, we can go ahead and figure it out. Say 32 times 1.6605 times 10 to the negative 27. 32 times that gives me 5.31, which is really one extra sig fig already. 5.314 times 10 to the negative 28 kilograms. Similarly, what we know about nitrogen is its atomic weight is 14. So we're going to say that's 14U, and that means its molecular weight N2 would be 28U. So we're now going to say 28 times 1.6605 times 10 to the negative 27th. In this case, I'm going to get 4.650 times 10 to the negative 28th kilograms. So again, I've got the non-significant figures actually underlined, so we'll know they're not there. But notice I am keeping the non-significant figures. You always keep at least one until the final answer. So now I'm able to figure out what the root mean square velocity for oxygen is. So VRMS O2 is equal to the square root of 3 times 1.3807 times 10 to the negative 23rd joules per Kelvin times 20 degrees Celsius is 293 Kelvin. So that's 293 Kelvin. All that divided by 5.314 times 10 to the negative 28 kilograms. And when I do this math, I'm going to go 3 times 1.3807 times 10 to the negative 23 times 293. And then I'm going to divide that by 5.314. Yes, 5.314 is the oxygen times 10 to the negative 28. And now I got to take the square root of that. And that number, by the way, I will go ahead and write it down. That turns out to be 2283845 So basically, that's like 22 million, and that comes out to meters squared per second squared. And when I take the square root of that, I should get around 480. I'm going to raise that to the 0.5 power, and that gives me 3 times 1.3807 times 10 to the negative 23rd. Got that. 293. Got that. I got off by a factor of 10, and I'm trying to figure out exactly why right now. 10 to the 28, 10 to the 28. Oh, aha. My vision is not so good. Those eights that I was reading were 10 to the 26. Had you noticed that? Either of you guys? Please help
Yep.
an old man out. I wrote these as 10 to the negative 28, when in fact they're 10 to the negative 26. I'm glad I caught it now, though. So there's that one. Now I'm going to do the same thing with this one. So that's 10 to the 26. Now I'm going to do the same thing right here. Okay, so that gives me 478 meters per second. And really, we only have two sig figs uh, because the 5.3 limited us. So that's basically the answer for the oxygen. Now we can do the same thing for the nitrogen. And in fact, I'm going to use a quick and dirty trick. VRMS for the nitrogen is going to be equal to the square root of 3kT over m, just like we did before. But what we'll notice is I can take and say, here's the velocity of the oxygen. So this would be the 3 kT over m, which actually I'll say lowercase m O2. But all we have to do is now take that and multiply it by the m of O2 divided by the m of N2, like this. So basically, I could take that 477.895. Ooh, I don't know what's going. Okay, hold on a second. I can take that 477.895 and I can divide that by, or excuse me, just multiply that by the square root of, basically, we're going to take the square root of 32 over 28. So it's going to be the square root of 32 over 28 times 477.895 meters per second. And 32, we cancel out the oxygen, and the 28 would replace it with the nitrogen. And that gives me 510.9 meters per second, which I'm going to say is 510 meters per second. And that one's for N2. So notice the nitrogen was actually a little lighter than the oxygen, and therefore its speed was larger because really, if two things are in equilibrium, their kinetic energy should be equal, not necessarily their velocities. The kinetic energy is the more important part. That's what actually, that's the energy transferred when two molecules run into one another. The faster one slows down a little bit, and the slower one speeds up a little bit, ultimately resulting in all of them having all the same kinetic energy. But any questions on that one? All right, so now that we've done that, you might want to have some idea of exactly what this root mean square is. So I'm going to show you how to calculate that. But before I tell you that, I'll let you know that your book does this example. It gets 480 meters per second as well, and 510 meters per second as well. But he takes the time to tell you that this is in fact around 1,700 kilometers per hour, or that's essentially 1,000 miles per hour. So that's how fast the molecules of nitrogen and oxygen are moving at room temperature. They're moving literally 1,000 miles per hour. So that's, faster than any of the cars that we have access to on the open road. We do have cars that have gone quite a bit faster than a couple hundred miles per hour. I don't think any of them's come near 1,000 miles per hour, but I could be wrong. So, any questions on that? Okay. Your book does do a conceptual example, which I want to talk about. It says a tank of helium is used to fill balloons. As each balloon is filled, the number of helium atoms remaining in the tank decreases. How does this affect the root mean square speed of the molecules remaining in the tank? If you look at the root mean square speed, you can see that it turns out to be 3 kT over m, which I'm going to circle right here just to remind you that that's ultimately the formula when we solve this guy for the root mean square velocity. So that only depends on temperature and the mass of the individual molecules. Therefore, if you are actually filling these helium tanks and you don't find that the tank is getting any colder or any hotter, then the root mean square speed should be totally unaffected. However, if you've actually ever used tanks to fill up scuba tanks or anything like that, what you will notice is when you're filling the scuba tank, it often gets hot. And if you're filling it from another tank, that tank often gets cold. So it isn't abnormal for the temperature of the tank that's doing the filling to change temperature to change as well. So in that sense, you would expect it to change, but only because it does depend on the temperature. So now I can go back to the next example, which is what is the average speed and root mean square speed. And in this case, it's going to be example 18.4, which I'm just going to call example 3 because it's the third example we're working. And what we want to know is what are the, or I should say, what is the average, what is the average translational speed? And really, the translational doesn't really matter here. I'm just talking in terms of the phrases we normally use, but we're trying to figure out what the average speed of particles. I don't want to word it like that. Well, let me just use their exact wording. Uh, I realize now that I'd read this before, but I was reading in the other edition and I'm not sure. Uh, the wording seems a little different from the third edition I was looking at earlier today. It says 8 particles have the following speeds. So here's the speeds. Those speeds are going to be one, and I should mention that they're in meters per second. And since I just erased that by accident, I'll just fix it now and say in meters per second. Those speeds are 1.0, 6.0, 4.0, 2.0, 6.0, 3.0, and 2.0 and 5.0. What are V and VRMS? So that's really what we're trying to compute. So let's start with solution. Now, what I want to remind you guys is that there's a couple ways you can look at average. We know, for instance, that X bar is equal to x1 plus x2 plus dot 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 on up to plus xn, where n is the total number. And then you add all those up and divide it by n to get the mean. However, another way you could actually say that is you could say the probability of getting x1 times x1 plus the probability of getting x2 times x2 plus the probability of getting x3 times x3, so on and so forth. That's another way of doing it, and that's going to come in handy when I introduce you to the distribution of speeds that we'll be using. The other thing we're going to do is we're going to take and find the root mean square. So in this case, x root mean square would be equal to uh, x1 squared plus x2 squared plus dot 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 plus xn squared. Now you're going to take all that, divide it by n, and that will give us the average of the square. But that would, for instance, if these x's were meters per second, then this would come out in meters squared per second squared. So to get the units right, we need to take the square root of it. And that's what the R is for. The R is for the root, the M is for the mean, and the S is for the square. So that's what we're going to do. So let's start off with V bar. So V bar is going to be equal to 1.0 plus 6.0 plus 4.0 plus 2.0 plus 6.0 plus 3.0 plus 2.0 plus 5.0, all of that divided by 8 numbers, which is good because I wanted to make sure I had that. So 1 plus 6 is 7, plus 4 is 11, plus 2 is 13, plus 6 is 19, plus 3 is 22, plus 2 is 24, plus 5 is 29. So this would be 29.0 divided by 8. And that gives me 3.625 meters per second, which notice the units do work out to be meters per second as we expect, but the 2 and the 5 are of course not real significant digits, so I'm going to put it circle it and put the 2 and 5 with underscores. Now we can calculate the root mean square, and the way we do that is as follows. VRMS is going to require us to take a square root, of course, and the square root is going to be of 1.0, which is squared is still 1.0, plus 36.0, plus 16.0, plus 4.0, plus 36.0, plus 9.0, plus 4.0 plus 25.0. In other words, I went ahead and squared each of them as I went, and I'm going to count them to make sure I didn't leave out any. So 1, 2, 3, 4, 5, 6, 7, 8. It is again. I'm going to divide that by 8, and again, I'll take the square root. Oh, well, after that. So 1 plus 36 is 37, plus 16 is 47, which is 53, plus 4 would be 57, plus 36 would be 87, plus 6 would be 93, plus 9 would be 102, plus 4 would be 106, plus 25 would be 131. 131 divided by 8 is equal to 16.375. All that divided by 8. So now I take the square root of that, hoping my arithmetic was right, and I raise it to the 0.5 power, and that gives me 1.4. Whoa, clearly I made a mistake. Let's double check my work. I'm going to say 1 squared plus.
You already divided it by 8, so it should just be
Oh, thank you.
square root of 16.375.
Gotcha. 16.375. And then the square root of that.
Correct.
Oh, gotcha. I see what, yeah, I forgot I'd already divided by 8. Thank you for that. What I'm going to do is do this. And what we're going to say, darn it, is let's erase everything by just letting my computer do stupid stuff. All right. So we're going to say the answer is, in fact, the square root of 16.375. And that gives me 4.04.
Yeah, that's what I got.
Or 6.6 or
Or
something like that. And this is good.
4.05, but
Yeah. So we're going to call that meters per second. But you can see how, of course, it's skewed a little bigger than the average velocity. Uh, and that is sort of the trend. The average of the square is generally larger than the average squared, if you will. So or squared and then take the square root, of course. So we got 3.6 for the average velocity. We got 4.0 for the root mean square velocity. That should make some sense to you. Anybody have any questions on that? And I think that was Josh talking, wasn't it?
yep.
That's cool. All right. Your book does point out that, this formula, the 3/2 kT, suggests, despite what you saw on the documentary called The Incredibles. So if you did see The Incredibles, you remember that the very first Incredibles had the bad guy who used to be the good friend of the good guy. and he made a 0 point energy device. And that's what we're talking about here. It turns out, quantum mechanically speaking, if you actually do go to the temperature of T equals 0, this classical formula, K bar equals 3 halves KT, predicts that the average kinetic energy should be 0. But in fact, quantum mechanics teaches us that that's not the case. It cannot, in fact, be 0. It has some minimal amount of energy. In this case, it turns out to be 1/2 h bar omega, which we'll learn about later. But the main thing is there is a minimum amount of energy that it can't really go less than, and that energy is not 0. Still, we use that, like I said earlier when we were talking about the Kelvin scale. If you made a plot of, let's say, volume versus temperature for all the substances or that you could make, and that means compounds, elements, and everything. If you put them all in a gaseous state and then you plot their volume versus temperature, they will all converge on a specific temperature if you allow the lines to be extended way past where they become no longer ideal gases or even gases at all. If you follow those lines out, they will all land on that 273.15 negative temperature. So it's negative 273.15 Kelvin, or excuse me, negative 273.15 degrees Celsius. So it's literally negative 273, or I should say it's literally 273.15 Kelvin below 0. Okay. All right. So we've now gotten through the kinetic energy being absolute 0. What I want to show you is what Maxwell came up with. So Maxwell, using statistical mechanics, which is probably the most relied upon and useful branch of physics there is. Kinetic theory is sort of a part of that, and statistical mechanics is another part. But you can just use the laws of statistics and compute a velocity distribution. And that's exactly what Maxwell did. So Maxwell, in 1859, James Clerk Maxwell, he lived from 1831 to 1879. But anyways, in 1859, he worked out the statistics of molecules and how much energy they have. And by so doing, he was able to come out with a distribution of velocities given by the following formula. So F of V, this means the probability in some sense of the particular molecule having a velocity V. Now, it also has to be normalized and all sorts of stuff like that, which it has been. That's why some of these numbers are out in front. But basically, the formula is 4 times pi times capital N, which capital N is supposed to be the total number of atoms or molecules that you're working with. All of that's going to be times m over 2 pi kt to the 3 halves power, and then times the square of the velocity times e to the negative mv squared over 2 kt. So you can see that's a 1/2 mv squared over kt basically. And what this means is if I multiplied this by dv, then the probability of finding a individual molecule with a velocity between v and v plus dv would be that quantity, f of v times dv. Okay, so just multiplying f of v times dv, you get the probability of finding something with a velocity between v and v plus dv. So in writing, this means f of v dv equals the probability of finding, whoa, dang it, a particle having a velocity between v and v plus dv. Okay, So what that's trying to tell you is that, hey, if you integrate from zero to infinity, then you've included all of the possibility, all the probabilities of the speeds that it could be. In other words, you've gone from one literally to infinity, and we know, for instance, nothing's going to go faster than the speed of light, but it's really not much difference in integrating this to 3 times 10 to the eighth than it is to integrating it to infinity. But when you do that, you get the integral of f of v dv has to be equal to the total number of particles because you've now done the probability of every speed, and therefore every particle must come out. So it's like that. Uh, in that sense, you should think, okay, I have f of v times dv. So that's the probability of finding a particle with a velocity between v and v plus dv. But now if you integrate that from zero to infinity, that means you've counted out every possible particle. That's why we got n out. Okay. So now that we have that, we actually have a way to do things like, well, what is the actual average velocity, or what is the most probable velocity? So let's work those. This will be example 4. Use the Maxwell distribution to find the most probable velocity. Okay, so we're going to start off with this solution. We know f of v is equal to 4 times pi times n times m over 2 pi kt to the 3 halves power times v squared e to the negative mv squared over 2 kt. Okay, the most probable velocity is the velocity that yields the max probability. So if we remember from our calculus days, maxima, minima, extrema are found by setting the derivative, the first derivative equal to 0, and then solving for it. And then if you want to make sure it's a maxima, then you want to make sure that the second derivative gives you a negative quantity. So I'm going to work that as follows. So let's say df over dv equals 0. Now, I know that all these multiplication factors out in front, they can't do anything to make it 0. So I'm going to pull them all out in front and say 4 pi n times m over 2 pi kt, all that to the 3 halves power. And now I'm going to say d by dv of v squared e to the negative mv squared over 2 kt. So this is a fairly straightforward uh, product that we have to take the derivative of. I'm going to call this big quantity C, and you're going to see that it doesn't matter because, as you can tell, we're setting it equal to 0. So we could divide both sides by C, and that's not going to matter at all. So what I'm going to do now is I'm going to just call this big C out in front, and I'm going to take the derivative of v squared, which would be 2v, and then I'm going to multiply it by the other factor, which is e to the negative mv squared over 2kt. And now, according to the product rule, remember you take the derivative of one and multiply it by the other factor without taking the derivative. Then you add to that the derivative of the other times the one that you didn't take the derivative of. So in this case, I'm going to put plus. Now I'm going to write v squared because we're not taking the derivative this time, but we are taking the derivative of e to the negative mv squared, which is the integral or the derivative of e to the u times du dv. So the derivative of e to the u is just e to the u, but the derivative of negative mv squared over 2kt is in fact negative mv over kt. And now I have to write e to the u, which is e to the negative mv squared over 2kt. And all that is equal to 0. Now you can see if I divide both sides by c, then I get a very straightforward result, specifically 2v minus mv cubed over kt, all of that times the common factor of e to the negative mv squared over 2kt, all that's equal to 0. The only way that can be 0 is if the parenthetical expression is 0. So I'm now going to say 2v equals mv cubed over kt, which means I can cancel, for instance, a v on each side and leave a 2 up there. And then what I'm going to get is v is equal to the square root of 2kt over m, and that turns out to be the most probable velocity, which is approximately equal to 1.414 times the square root of kt over m. Okay. Now that is our most probable velocity. If we want to go a step further and confirm, in fact, that that is a maxima, then we have to take the second derivative of the function and show that that's in fact a negative. I'll leave that as an exercise for you guys to do, possibly even extra credit if you want. If you do decide you'd like to do that for an extra credit, then I'm also going to allow you to use, for the extra credit, you can do that part, plus you can do integration by parts to figure out the next one, which is what we're going to do to calculate the average velocity. So any questions on this one? So if you were to make a graph of that Maxwell distribution, it would look like this basically. So if you put your velocities here and you put your probability of velocity here, what you would see is the graph sort of comes up kind of quickly, crests over, and then falls off gradually. It shouldn't have that non-smooth part there that I just screwed up. In fact, let me just fix that a little bit. So this should come over and reach a peak and then come down like this. What we just found was the VP would be right there. What we can also find, though, is a little bit to the right of that would be the V root mean square. And a little bit further to the right of that would be what we'd call V bar, which is what we're going to calculate next. So any questions on that before we move along?
Wait, I think the V bar is in between the RMS and VP.
That could be right. Let me double check. Oh, yeah.
I'm looking at the graph in the book. That's the only reason why.
Yeah. Yeah. Actually, I was going off my head. I should have checked.
No, you're fine. I was just trying to make sure.
Yeah, no, I appreciate it. That it's always good when you make when you correct my errors. That definitely helps me and it doesn't offend me at all. So thank you. So yeah, V bar is here, and then V root mean square, which I should have known because really the neat part about this is VP turns out to be the square root of 2 times the square root of KT over M. So that's 1.414. If you look at the actual one for the root mean square, that turns out to be the square root of 3, which we already did. So that's 1.73. And then the average one turns out to be 1.60, which is like the square root of 4 over pi or something. So let's go on to the next part, which I'm going to call
Hey,
example.
Professor Younger, just
Yes.
one question. Could
Mhm.
you explain again how you were able to pull out that first term to call it, and you called it C
Okay.
from df
So
over dv?
notice you're taking a derivative with respect to v. And strictly speaking, this you can either look at this as a function of one variable, and that variable would be v, in which case you're just taking the derivative with respect to v, and the m and the n and the k and the t do not depend on v. So all of those terms, the 4, the pi, the n, the m, the 2 pi kt, all of those are just constants. So they would come out in front. And all you're left with to take the derivative is the derivative of v squared times e to the negative mv squared over kt, over 2kt.
Yep,
Does that
yep,
make
got
sense?
it. That
But since we are multiplying the velocity to whatever to mv squared over 2kt,
Hmm.
we then have to take the derivative of that though, because v is
Exactly.
associated with all those.
Yeah, because there is an explicit v in the exponent of the exponential.
Yeah,
So what we're looking at is we have a v squared, and then we have this exponential, both of which are functions of v. So you have to take, for a product rule, you have to take the derivative of the first one times the second one plus the first one times the derivative of the second one. But the chain rule dictates that the derivative of e to the u is the derivative of e with respect to u times the derivative of u with respect to v.
right.
Does that make
Okay.
sense?
Yep.
Did you have a question in there that I missed, Josh or Matthew?
No, I was just, I guess, just clarifying since v is included with all of those other constants,
Right.
v is dependent on that. Or I
Yeah.
should say the,
Yeah. It
yeah,
gets a lot more complicated if you're thinking V depends on T or T depends on V or something like that. Then you got to do a lot more stuff. But luckily, the laws of physics turned out to be as simple as they are to some extent. Maxwell's
right.
distribution works really well, at least in the realm of the ideal gas laws. It works really well. All right. Anything else? All right, so example 5, we just used the Maxwell distribution to calculate the most probable velocity. Now I'm going to use the Maxwell distribution to calculate the average velocity. So this will be example 5. Use the Maxwell distribution. I often forget to cross my T's. That's a danger. So just be aware of that. Use the Maxwell distribution to calculate the average velocity, which is what we call V with a bar over it. Okay. Now, this is something where you're going into some calculus-based statistics and probability. So just for the record, you need to know this. And that's sort of the reason why I was telling you there's two ways to look at the mean. I said you could look at it as x1 times the probability of x1 occurring plus uh, x2 times the probability of x2 occurring plus x3 times the probability of x3 occurring. That's what we're doing here is we're imagining multiplying a particular velocity v times the probability of that particular velocity f of v. And then we're adding them up, only we're allowing the v to change by an infinitesimal amount. And therefore, we're doing a Riemann sum and therefore an integral. So v bar can be written as the integral of f of v times v dv. Similarly, if you wanted to know the average square of the velocity, you'd multiply by f of v times v squared, and so on and so forth. So that's really what we're shooting for here. I'm looking, yeah. So you have to take those probabilities, but then you also have to divide it by n because this is going to give you something that's related to n. So ultimately, what we have to do is we take this f of v integral, or excuse me, integral f of v times dv, and then divide that by n. And specifically what we're doing is we're taking the integral from 0 to infinity because we have to account for all of the possible speeds. So that's the way you'd calculate the average velocity. And just for the record, if you wanted the average of the square of the velocity, which is where the root mean square comes from, you would take the integral from 0 to infinity of f of v squared dv, and again divided by n. And then if you wanted the root mean square, you'd have to take the square root of that. Okay. So let's work with V bar. So V bar is going to be 1 over n times the integral from 0 to infinity of 4 pi n times m over 2, it's 2 pi kt, to the 3 halves power times, now not v, but v cubed. It was v squared before, now it's v cubed, times e to the negative mv squared over 2kt dv. Okay. Now we know that we can, for instance, pull out all those constants out in front, and that's what we're going to do. We're going to say this is all equal to 4 pi n times m over 2 pi kt to the 3 halves, all that divided by the n that we already had, times the integral from 0 to v, or excuse me, 0 to infinity, of v cubed e to the negative mv squared over 2kt dv. Now, what I do know is you can look in the appendix. That's one of the integrals they have in the table. So I'm going to do this in an entirely different color just so we'll know that it's not the mainstream calculation. But what we know is there's an integral from 0 to infinity of x cubed e to the negative a x squared dx, and that turns out to be 1 divided by 2a squared. So what I need to do is convert that that a to what it is in our particular problem. So I can, for instance, let's let a equal m over 2kt, like that. And that should do it. So now I'm going to go ahead and say that. That looks okay with me. The v squared is there. That's okay. So I'm going to say well, I'm going to put all that other stuff in front, which, by the way, the ends did cancel out. So I'm now left with just 4 pi. Actually, it should be all be on one level, so I don't really have to write it like it's a numerator. It's going to be 4 pi m over 2 pi kt to the 3 halves power times the integral from 0 to infinity of v cubed e to the negative a v squared dv. So that all looks good. We've got the right variables and all that good stuff. So now I can say this whole result should be 4 times pi times m over 2 pi kt to the 3 halves power. And this whole integral is going to be 1 divided by 2. Now I've got to take my a and square it. And my a was m over 2 kt. I'm going to square that. So I'm now going to have 4 times pi times m over 2 pi kt to the 3 halves. And I'm now going to have 2 kt squared over 2 times m squared. Now that I have that, I could go ahead and combine these by, for instance, putting all that stuff inside of the parentheses by squaring it. That would make it, if I squared it, that would allow me to put it under the square root, and then I'd have to, of course, cube it as well to do that. But we can look at it this way. So I've got 4 times pi. I'm going to do it sort of term by term just to keep our wits about us. But what I have is a m to the positive 3 halves, and then I have a m to the negative 2. I have a 2 pi to the negative 3 halves, and a kt to the negative 3 halves. And I also have a 2 to the negative 1 and a 2 to the 2 and a kt to the 2. So I've just sort of broken down all the junk I have. Now that I have common bases, I can actually combine them. So I have a 4 times a pi. I have a m to the 3 halves times n to the negative 2. So when you multiply two things to a power, you add their powers. So 3 halves minus 4 halves, because negative 2 becomes negative 4 over 2. So negative 3 halves plus negative 4 halves. So 3 halves plus negative 4 halves would be negative 1 half. So that should be m to the negative 1 half. That takes care of this guy and this guy. The 2 pi, I could actually change that a little bit. I'll deal with that in a second, so I'm going to leave that for right now. But let's look at the kt. I've got kt to the negative 3 halves and kt to the 2 power. So 2, which would be 4 over 2, minus 3 over 2 would be 1 half. So we're going to have kt to the 1 half power. That takes care of this kt and this kt. And now I can go ahead and write this 4 as 2 squared. And this pi as pi to the 1. But we also have 2 to the negative 3 halves. And we also have pi to the negative 3 halves. And that takes care of that 2 and that pi and that 4 and that pi. And it looks like, we also have a 2 to the negative 1. So that takes care of that one. And that should be all of it. Now I can see 2 squared times 2 to the negative 3 halves. That'd be 4 halves minus 3 halves would be 1 half. Minus 1 would be negative 1 half. So this is going to be equal to 2 to the negative 1 half. We have a pi that is to the 1 power. minus 3 halves. So that's 2 halves minus 3 halves. That'd be negative 1 half. So it'd be pi to the negative 1 half. We've got m to the negative 1 half. And we've got kt to the positive 1 half. And that looks like we've taken care of everything. And sure enough, our answer is going to be equal to, all of them have a 1 half. So I think we can see that it's going to become a 2 to the negative 1 half. Is that right? Negative 3 halves minus 1 would be negative 3 halves minus 4 halves. So that would be negative 7 halves plus 4 halves. Oh, yeah, so that one cancel out anyway. So 2 to the 2 times 2 to the negative 3 halves would be 2 to the 4 halves times 2 to the negative 3 halves, which would be positive 4 halves. Minus 1 would be, or excuse me, positive 1 half. Minus 1 would be negative 1 half. So the 2 does turn out to be on the bottom. And the pi turns out to be 1 minus 1 half. Oh, 1 minus 3 halves. So that's 4 halves, or 2 halves minus 3 halves is negative 1 half. So it's 1 over 2 pi, maybe? Oh, wait a second. I might have made a mistake with the 2 squared. I'm going to go ahead and write this to the side to make sure I don't make any careless mistakes. So I've got 2 to the 2 that came from this one. I've got 2 to the negative 3 halves that came from this one. And I got 2 to the negative 1 that came from this one. So this should be 2 to the 4 halves minus 3 halves minus 2 halves. So that's 2 to the 4 minus 3 is 1 minus 2 is negative 3. 4 minus 3 is 1. Darn it. I've lost it. That sound didn't help me. But ultimately, I should have had 8. Ooh, let's go ahead and write it in here. There might be a arithmetic error somewhere in here, but it should have came out to be 8 over pi times. Notice everything else did work. So remember we had 3 kt over m. In this case, we do get a k on top. We do get a t on top, and then we do get an m on the bottom. So all that part works. And this is approximately 8 over pi is about 2.54. And when we take the square root of that, that gives me about 1.60 or 1.5958 times the square root of kt over m, which is v bar. So that's the ultimate answer. I may or may not have been able to come up with that 8 over pi. I know I've done it in the past, but I probably dropped something somewhere. If any of you guys see that, let me know. Oh, that's where it is. Yeah, I left off that 1, 2 down there, so that might have been the problem. But anyways, that's the second example. Anybody have any questions on that? Okay.
Nope.
So you can see, as I mentioned earlier, you can go ahead and take the second derivative of that probability function like I did before. Take the second derivative and then plug in that specific value of v that I gave you, which was what, the square root of 2kt over m. Put that in the second derivative and see if that you get a negative. That will convince you that it is, in fact, a maxima. And you can also then use the integration by parts to do the integral that we just did, as opposed to using the integral table like I did do. Okay. That's just a good practice for you guys to do, especially if you haven't used integration by parts a lot. That's a fundamental idea that you should be able to do. So that'll be extra credit. I'll type it up and put it in the week 2 module. But I think we're in a pretty good spot right now for finishing up. We've basically finished section 18.1 and 18.2. 18.3 is more of a conceptual section. You really need to read it thoroughly. I'm not going to cover too much of it, but you can look at such things as what these three-dimensional graphs might look like when you do pressure versus volume, and maybe add a third dimension that might be temperature or something like that. That's what all these different graphs are, and they show the different states that they're in. So, for instance, to the left of a graph, you'll have solid, and down to the bottom right of a graph, you'll have a vapor, and then in the little V of the graph, you'll actually have liquid. So all of that is talking about how matter behaves and so on and so forth. So definitely read it over. I'll sort of do, give it really short shrift and talk about it next time, but that's basically it. So we'll go on next time, starting in section 18.4, and I'll finish the rest of the examples in the chapter, at least the sections that we're going to do. And you guys will be finished with chapter 18 and ready to move on again. So keep an eye out for my videos on the ideal gas law. And I've already put two of the videos up on linear expansion. But you guys are free to go. Thanks for coming, and feel free to ask me any questions. I'm going to wait for the last person to leave before I shut down. And I know Matthew's got some questions about chapter 17, so I'm ready for that whenever, Matthew.
Okay, thanks. Just two questions on the homework that were giving me problems.
Okay.
I guess the first one was on 17.3.4. And if this is in the video, I haven't checked out the video. I can go review the video.
Oh, that's okay. It
Uh,
probably isn't, but yeah, 17.3. I can pull that up on my side, but would you like to share it via your screen?
yes, I could. Hold on one second. Let me pull it up.
I just made it where other people are allowed to share, but I don't know from your side what it looks like to share. There should be some little button down there that allows you to share a screen.
Okay. Yeah, I will figure it out.
I'm gonna head out. Thanks.
All right, no problem, Josh. Thank you, bud.
Yep.
Okay. Where should I see that button to share?
Uh, do you have any little arrows pointing up anywhere around the edge of your screen at the bottom of your window, or this left side or the right side, or a more
Uh,
button, for instance?
oh, share. Yeah, right there in the middle, the green one, the bright green
Okay.
one. Okay.
So it does look like mine. It's just a bright green button. I'm going to go ahead and type your name in the chat because that's what I do to check roll.
Okay.
The roll doesn't matter in this, but that's what you want to try to do every time you pull it up, or every time you log in and take class.
Okay. Just have so many windows open. I'm trying to figure out which one to actually share here.
Are these dots all places you've been?
Yeah.
I'm jealous. I haven't toured America very much at all.
Okay. Do you see that 17.3.4? Is that the one that's being shared?
I'm seeing your desktop with all the countries and the
Okay.
map of America. That's what I'm seeing right now. So you might
Oh,
just use a different
that's
window.
my VPN then. Okay.
Sometimes there's a little arrow next to the share, and that gives you a list of things. Or when you click share, sometimes it'll have little tabs in the window where you can click to the whole screen. Oh, there you go. You nailed it. So this is
Okay.
1734.
Yes.
Okay, and it says there's 16 moles of helium gas at 11 degrees Celsius and a gauge pressure of 0.390 atmospheres.
Yes, I think it's a fairly straightforward problem, but I'm not getting the answer, and I think it's because I don't know. I don't think I'm using the right P.
Now, did you remember to add 1 atmosphere to that? So when they say gauge pressure, that means the pressure minus 1 atmosphere. So one, the total pressure is what you have to put in the ideal gas law. So that would be 1.390 atmosphere. But then here's the other kicker, which you might not have thought about. When you're using the ideal gas law, you have to make sure you use the right version of R for the units you're using. So for
Okay.
instance, when you're using atmospheres, you should use 0.0821, and that's in liters times atmospheres per mole Kelvin. So I'm thinking that's the one that you want to make sure you're using.
Okay. So the equation would then become I would say the n equals 16 moles in the numerator times that 0.0821 liters per atmosphere over moles Kelvin. Or I'm sorry, liters atmosphere per moles Kelvin times 284 Kelvin, just as a general setup, and then over what the pressure would be. So if I add the atmosphere, that's the 0.390 gauge pressure plus 1.013 times 10 to the fifth.
Yeah, that should be. Oh, no, no. You can use it straight as atmosphere. So you're just going to type in straight 1.390.
1.390. Okay, so I'm just adding 1 atmosphere.
Exactly.
Oh, okay, got it. So then just gauge pressure becomes, and what's the terminology? Is that absolute pressure?
Yeah, it's
If
absolute pressure or gauge pressure. So gauge pressure's the pressure minus 1 atmosphere, and absolute pressure is the gauge pressure plus 1 atmosphere.
Okay, got it. And if I'm using that absolute pressure after adding the atmosphere to the gauge pressure, then I use the 0.0821 for R.
Mhm. Yep.
Okay. All right. Sounds good.
And that'll come out, by the way, in liters, not cubic meters. So you've got to then convert that. So I get 268 liters.
Okay. You said 268 liters, and then I convert back
To cubic
uh,
meters.
to cubic meters. Okay. How on earth would I convert back to cubic meters? Is that
The a liter is actually defined to be 10 centimeters by 10 centimeters by 10 centimeters. So if you realize that, that's 1,000 cubic centimeters. So a cubic centimeter has to be a milliliter, and that it actually means that the liter is basically right in between the cubic centimeter and the cubic meter. But you can also just look up what the
yeah.
conversion is.
Yeah, I'll figure that piece out. That'll get me there. I was on my last attempt there, so I didn't want to risk it.
I'm
Okay.
doing on my calculator real quick for you so I can check, and I want to put that in cubic meters. So cubic meters plus that turns out to be 0.268. Like I said, it was 1,000. So 0.268 uh, should be the cubic meters for that one.
Okay.
11 plus 273 should be 284. Yep, that's what I did. I did 284 times 16 times 0.021 or
Point.
0.0821, and then divided it by 1.39, and that gave me the 268. And basically, a cubic meter is 1,000 liters.
Cubic meter is 1,000 liters.
One
Okay.
cubic meter is 1,000 liters.
Okay. Got it. So I'm just really dividing by 1,000
Yep.
to get it back. Okay. All right.
This is actually
Great.
a really good question. I'm glad you asked this because I didn't make a video on this yet, but did you do the intro to the ideal gas law tutorial yet in that homework set?
Um, in the homework set, was it one of the problems you mean?
Yeah, it should be. I think it might be
Yeah.
listed as the last one or the first one of the two, but it says
Yeah,
intro to the ideal gas law.
yeah, I've done all of them except for this one here
Okay,
and the additional.
cool. Yeah, that's where he's trying to do what he did in the book, which is explain that, yeah, you've got to use it in Kelvin at the temperature, which you knew that part. The only part you probably didn't know was about gauge pressure. So that's
Yeah,
certainly understandable. Just if you think about it, have you ever seen how a tire gauge works? Well, you probably have, I'm
yeah,
sure. That's literally a tire is open to the atmosphere and it's pushing against the atmosphere. Hopefully,
okay,
that sort of makes you understand why the gauge pressure is literally different from the atmospheric pressure. I mean, the absolute pressure by 1 atmosphere, because that's what
yeah.
it's fighting against to get out.
Okay, great.
Right.
Um, and then one additional question, and I actually got this answer correct. Well, almost all correct.
Hmm.
1755, but I have to confess, I more or less guessed to get the right. It was just off by a factor of 100, I guess. Uh,
Hmm.
and so let me look at this problem again. At such pressure, how many molecules are there?
Per
Um,
cubic centimeter.
yeah,
Ah. So what you're asked for there is really N, the big N, not Avogadro's N, but big N. And remember, there's another way you can write the ideal gas law. Instead of PV equals lowercase n times R times T,
yep,
they're sort of expecting you to use P times V equals uh, big N times K times T, and you just solve for N over V, and that'll give you atoms or molecules per cubic meter or per cubic centimeter.
okay.
So let's try that. You got three
Nice.
degrees Celsius. How many molecules are there? The lowest pressure attainable using the best available vacuum techniques, 10 to the negative 12th. Okay. So I'm going to work that on this side and see if I get the same answer you did. Uh,
Okay.
I tell you what, let's see, this was 3 degrees Celsius. And the pressure was 10 to the negative 12th newtons per square meter. And we want to know N over V equals question mark. I'm going, and you said the answer was 263.
Yep.
That's molecules per cubic centimeter. Okay. I'm going to steal the screen for a second and write it up here and see what we come up with. Is there any other data that it gave us, or is that just it?
That's it.
Okay, that's cool. All right, so I'll do share my screen and I'm going to share my iPad and I'm going to do this, which should pop up any minute now. Okay, so what we're looking at here is the ideal gas law you had used earlier was this one, PV equals nRT, but towards the end, so that they can do this derivation that I skipped in chapter 18, they let you know that you can also write this as big N, where N is the total number of particles, times K, the Boltzmann constant, times T. All the other rules are still in place, so you still got to use the temperature has to be in Kelvin, the pressure has to be absolute pressure, not gauge pressure, all that good stuff. But in this case, they're asking for the number of molecules per unit volume. So they're just begging you to solve for N over V, which you can see N over V should be P over KT. So, and that might come out depending on that actually will come out in molecules per cubic meter, more likely. So N over V is equal to P, which they said 10 to the negative 12th newtons per square meter, which is a Pascal, by the way. K is 1.3807 times 10 to the negative 23rd joules per Kelvin. and T was 3 degrees Celsius, which means 276 Kelvin. So if I do that math, I'll say 1 e to the negative 12. Watch out for that, by the way. If you type in 10 times e to the negative 12, that's actually going to be off by a factor of 10. So
Okay.
I type that in as 1e negative 12. But that's a common mistake students make, so just keep an eye on that one. 1.3807 times 10 to the negative 23rd times 276 Kelvin in the bottom. That gives me 260 or 2.624 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th, and that should be molecules per. Now, if you worked out those units, it does turn out to be per cubic meter. And what you do is you say, well, 1 meter is equal to 100 centimeters. And then you got to remember that that's actually cubed. So you've got to cube this as well. So you're basically dividing that number by a million. So it becomes 262.4 molecules per cubic centimeter. And you got what, 263?
Well, I did, but that was kind of a guess with the power. And so I
Yeah.
think what the mistake I made was with what you mentioned. So 10 to the negative 12 should be written as just 1 e
Yeah.
to the
What
negative 12.
my
Okay.
calculator has the button that says times 10 to the x. So my button looks like this. Other ones look like this, and other ones
Okay.
look like this. But 10 to the negative 12 should be put in as 1 EEEXP or times 10 to the x. Whichever button you have, you then type in negative 12.
Okay.
But yeah,
Yeah, I'm
I
actually
was
not
wondering if
seeing
that was your mistake.
yeah, I think it was. I'm not seeing your screen, by the way, but I
Oh,
think
yeah.
I understand
Oh,
what you
gotcha.
want me to do.
You have in that window where you were sharing, you should have something that gives you a bunch of different choices of what you're wanting to look at. So you probably can find like a little arrow that you can click on and it'll give you other choices, and that'll show it to you. It's showing on my side, so it will be on the video at least. So if you can't find it, you'll at
Okay.
least see it at the end of the video.
Yeah, sounds good. I think I got it anyways, but hold on here. So let me rework it. 1, 2, 3, 4, 5, 6, 8. So basically I'm just moving that decimal 6 places
Hmm.
when I convert it back from centimeters cubed to meters cubed. And that was the mistake, is that I was entering that would be the wrong pressure, off by a factor of 10. Okay.
And you just remember, like when you're doing the ideal gas law, you do have to use absolute pressure. And if you're using units of atmospheres, that means you just add 1 atmosphere. But if you're using Pascal, you got to add the 1.02 times 10, or excuse me, 1.01 times 10 to the fifth Pascal.
Sorry, could you repeat that very last part about Pascal's?
If the pressure has to be the absolute, so
Yep.
if you're given a gauge pressure, you got to take the gauge pressure and add 1 atmosphere to it if they gave it to you in atmospheres. But if they gave it to you in Pascal or newtons per square meter, then it's added to 1.01 times 10 to the fifth Pascal, or newtons per square meter. A Pascal and a newton per square meter are the same thing.
I'm sorry. One more thing. So you said for pascals, I multiply times
Oh no,
1.05.
you add.
You add.
So
Okay.
yeah, if someone gives you the gauge pressure and they give it to you in newtons per square meter or
Yep.
Pascal, then you add 1.01 times 10 to the fifth newtons per square meter or Pascal. If they give it to you in atmospheres, then you add 1.0 atmosphere.
Got it. Or they might just give absolute, right?
Yeah, if they don't say gauge pressure, then they're probably giving you absolute pressure. The only way they kind of sneak it in is when they actually say the reading is, and they're showing you a picture of a gauge. So
Okay.
sometimes they'll say, "Oh, you got to be smart enough to realize, hey, you're looking at a gauge, dude."
Yeah. Okay. All right. Yeah, that makes perfect sense.
All right, did you
Got
ever
it.
see the screen?
No, I didn't, but I got it.
All right. Well, whenever this is up, which should be in the next hour, just take a screenshot of the last page if you want to, or the last
Yeah.
scene. So
Yeah.
thanks, Matthew. I
Yeah.
appreciate you coming.
Okay. Yep. Thanks a lot.
Have a
Thank
good
you.
day.
Yep.
Bye bye.
Bye.
Bye, everybody. Thanks for coming. Both of you.